Hi everyone, my name is Ruixuan Wang. I'm from Department of Biostatistics in University of Michigan. Today my topic is asymmetric integration of various cancer data sets for identifying risk-associated variants in genes. First is the introduction. In nowadays researchers, cancer remains the leading cause of deaths in the US and globally. Genetic or genomic data can help improve cancer diagnosis and enable personalized treatment plans. Many cancer data sets are rare, leading to small sample size in individual studies. So now scientists are doing the pan-cancer analysis. They integrate data across cancer types and increase the statistical power. They identify shared genetic pathways across cancers. The motivation of our study is to integrate additional cancer data sets for each cancer data set and increase the sample size and then enhance the statistical power. We extract case control genotype data from Michigan Genomics Initiative. A novel asymmetric data integration method assigns data adaptive weights to accelerate data sets determined by minimizing the leave one out cross-validation error in the primary data sets. We adapt, extend, and apply this method to identify potential genetic variants and genes that are associated with cancer risks. So now we have a data set. We have the genotype and the case control status. We use the genotype as the covariate and the case control status as the outcome. And then for this kind of data, we usually use the conditional logistic regression to get a non-integrated p-value in our study. And then we have a lot of the external data sets. So we use the data from both the external data sets and the local data sets, and then got some estimation information, such as the X transpose X and X transpose Y. Then we minimize the leave one out error to get integration weights. With the weights, we did a weighted conditional logistic regression for the whole local data and external data and get the integrated p-values. So what is the leave one out cross-validation error? The leave one out cross-validation error is the leave one out likelihood of the leave one out parameter estimates estimated by the log likelihood of the leave one out parameter estimates. The leave one out parameter estimates is the estimate that maximizes the leave one out log likelihood. So we then got the weights for each external data sets by the optimization of this leave one out estimate. Then here is our data set. We use the Michigan Genetic Initiative data set with the freeze-4 cohort. The Michigan Genetic Initiative data is from the University of Michigan Hospital. This is an upgrowing biobank. We use the case control data, extracting 14,000 patients with 7,000 matched strata, and we extracted 14 cancers, which are listed in Table 1. These 14 cancers are the most prevalent cancers in all the cancer data sets. The matching criteria of our data are gender, self-reported race, age, and zip code. It has to be mentioned that we only use the self-reported race, so we did not did any population stratification in our data. The genomic data are common variants that have the minor allele frequency greater than 5%. So this is about 6.2 million variants. The genotype data are alternative allele dosage with a continuous variable ranging from 0 to 2, indicating the number of minor alleles at that position. And so this is our pipeline for both the integration method and the non-integration methods. We pick one from the 14 cancer data sets as local data set, and then construct conditional logistic regression models for each local data set. We collect the p-value of the word test, and then we call this p-value as the non-integrated p-value. And then we filter the variants with p-value less than 0.05, and then use the rest 13 cancers as external data sets and undergo the integration methods. Why we are doing the filtering step in this here is because we have a very huge data, and the computation time is very long for us. If we do not use the filter step, it will take like over months, like several months for us to compute on the cluster. So after this, it still takes like 1 month to calculate all the things on the cluster. And then we get the assigned weights for external data sets, and then construct the weighted conditional logistic regression for all 14 cancer data sets. And we save this p-value of the word test as the integrated p-values. Then we repeat the step 1 to 6 for all the 14 cancers. However, we recognize that our integrated p-value is actually inflated. From the QQ plot of the integrated p-value and the theoretical p-value, you can see that it goes very far from the red line, and it has a genomic inflation factor of 2.5, which is much greater than 1. So this raw integrated p-values is biased and anti-conservative. It is because the conditional logistic regression assumes fixed weights rather than weights adaptive to the data. Then we want to do the false discovery rate control. However, there's many common used false discovery rate control method. One is the standard FDR control procedure, such as using the Benjamin-Hochberg. We cannot use this because we are using the genotype data. The genotype data are not independent with each other. There are linkage, disequilibrium, and population stratification within our data. For the traditional permutation tests, it can be used in our data, but as I mentioned before, our data is very time-consuming to compute the integration value, to compute the integration p-values. If we use the traditional permutation tests, it will take us tens or hundreds of times to compute. So then we find another method, which is called the single iteration permutation method. This is a preprint article. So we did some like the simulation tests of this method. This method have a pretty good statistical power on our genotype data. Like the statistical power is 0.8 over 0.8, but its false discovery rate is not as good as expected. It is like 0.2 to 0.3. But it is a kind of a trade-off between the computational time and the false discovery rate. So here's our final pipeline. We swap the case control data to have the permutation to have the permutated data, and then calculated the FDR. The case control status was swapped with 50% probability. So the permutation data is kind of the null data. And then we calculate the false discovery rate of each variant by the number of p-values in the permuted data set that is less or equal than the p-value of the variant, divided by the number of p-values in the original data set that is less or equal than the p-value of the variant. And because the false discovery rate is less or equal than 1, so we add a minimum of 1 in this formula. It should be noted that if there's p-values in the permuted data set that is if there's no p-values in the permuted data set that is less or equal than the p-value of the variant, then we could get FDR equals to 0 by the equation. But this is not conservative. Actually, we don't know the exact p-value of these variants, and so we would denote them as less than the smallest non-zero FDR of the whole data set. And here's the result. Here's the Manhattan plot of the bladder cancer, because we have 14 cancers. We each one have one Manhattan plot, and we only present one here. If you compare the left and right column of the plots, this is the integrated data set and non-integrated data set. So you can see that there's a significant inflation of the integrated p-values. That is the same conclusion from the QQ plot. But if you compare the top and bottom Manhattan plot, so you can see that there's not significant difference between the permuted p-values and the non-permuted p-values. So we need to calculate the FDR to find which variant is significant. Then we calculate the FDR of each variant and make this plot. So we use the 0.1 as the threshold, and you can see that there are a lot of points that on the right bottom, that means this variant is significant in the integrated method. But on some dots on the left top, it is the variance that's significant in the non-integrated FDR. So you can see that there are more dots in the right bottom. It means that our integration method find more significant results. Another thing is that although we have 14 cancers, we didn't find significant variants in all the 14 cancers. We only find them in 11 cancers, and some of them is in integration methods, and some of them is in non-integration methods. Some of the variance is only significant in the non-integrated method because the non-integrated method is a not biased result, but it can be explained because if this variant is only related with one cancer, so it may not be significant within the pan-cancer study, because in the pan-cancer study, we want to find that this variant is related with all the cancers, not only one cancer. And here's the final result of the number of variants discovered in the FDR threshold. It looks like there are more numbers than the points in the plot below the plot before, because there are some dots in the plots that overlap with each other. So there might be like several variants within each dot. We utilize the linkage disequilibrium clumping after we find the significant SNPs to remove the duplicate SNPs. And then we identify the neighboring genes in the dbSNP database. We validate our findings by comparing them with the data from GWAS catalog, UK Biobank FIVAB, and MGI FIVAB. Of the 72 significant genes from the integrated analysis, 10 are validated with significant relationship with cancers. All of them are breast cancer. This mainly because the breast cancer has the biggest dataset size of our whole cancer. Like we have like 14,000 samples, but only the breast cancer, it takes like 2,000 samples. So it takes like much proportion of our whole data. And for example, there's one variant, which is RS4784226, which is located on the chromosome 16. It is a 2000 base pair upstream variant and upstream transcription variant of TOX3 gene. TOX3 gene is a known gene that is related with breast cancer. The integrated FDR of this variant is less than 0.03, and the non-integrated FDR of this variant is less than 0.5. This FDR is calculated with the breast cancer. And this result is validated in both UK Biobank FIVAB and the MGI FIVAB. We also want to know how our where our significant SNPs are located. So we also calculate the distance to the nearest transcriptome start site. For the background TSS result, we randomly select 1,000 SNPs from our 6.2 million SNPs, and we make the density plot of the TSS as the plot here. So the red one is the density of the significant SNPs, and the gray one is the background. You can see that it seems that the red one is more concentrated in the middle, that it had higher peak in the middle, but the gray one is lower. To test our findings, we use 500,000 base pair as the threshold to categorize the TSS distance. Then we use a chi-square test, and we find significance difference in randomly selected SNPs and significant SNPs with the p-value less than 0.001. And now here's our conclusion. We developed a novel asymmetric data integration method for matched case-control cancer data analysis. This method integrates data sets from different cancers and fit conditional logistic regression models with data adaptive weights. Integration methods reviews an increased number of significant findings of potential cancer risk associated common and related genes. Many of these genes have been previously identified in the cancer literature and thereby supporting our findings. For the future work, as we only use the common variants, we also want to use the rare variants that have the minor allele frequency less than 5%. We have tried the burden test, but it does not work very well, so we might try other methods. And we acknowledge that the single iteration permutation method has a higher false discovery rate than we expected. So we are thinking about using other methods, but we still have to adapt for our computational time. Thank you, that's all.